I'm David Snyder, an environmental engineer serving as the Chief Operations Officer of Deep Green Solutions. I'd like to talk with you about climate restoration using a natural process. The world needs to reduce carbon dioxide in the atmosphere, and replicating what happens in the ocean after dust storms and volcanoes seems like the way to go. We do need funds to support tests in the ocean. Deep Green Solutions is a California-based nonprofit, and we're leading the way to develop this technology. With your help, it can be done economically and at scale. Our work is based on J.H. Martin, an oceanographer who in the 1990s observed that an increase in dust storms over the ocean leads to increased phytoplankton growth. This is because phytoplankton are normally iron deficient and the dust brings iron. Phytoplankton photosynthesis captures large amounts of carbon dioxide, and some of that carbon gets deposited deep in the ocean. In addition to dust storms, iron is replenished by volcanoes, ocean upwelling, and whale poop. Our name for this is phytoplankton carbon dioxide removal. Here is the Keeling curve, which shows the level of carbon dioxide in the atmosphere as it is monitored in Hawaii at the observatory at the top of the Mauna Loa volcano since 1958. We know that in pre-industrial times, carbon dioxide stayed pretty much below 300 parts per million in the atmosphere, but today it's over 420 parts per million. And as CO2 in the atmosphere goes up, pH in the ocean goes down. This is called ocean acidification. Here we have the CO2 in the ocean going up and the pH going down. And this is bad for a lot of habitats and species that are acclimated to what was the normal pH in past times. The Keeling curve shows that in 1991 to 92, there was an effect from the volcanic dust that went into the South China Sea from the Mount Pinatubo volcano. You can see the red dotted line showing the trend going up from year to year, but there was a pause in that increase as carbon dioxide was captured and sequestered in the ocean. And then after a while, that effect wore off and that constant climb in the concentration resumes. So here's where we are today. There's an excess of about 1,000 gigatons of carbon dioxide in the atmosphere. And if we remove carbon dioxide from the atmosphere at a rate of 60 gigatons per year from 2030 to 2050, we should be able to get back down near that pre-industrial level. We'd like to do a pilot project to confirm this method. This involves sending a ship around within a project area, distributing iron dust repeatedly during the project. The phytoplankton take in the iron and are able to grow more than they normally do. Nitrogen-fixing organisms also grow, helping to sustain the phytoplankton as part of the whole carbon cycle and growth cycle in the ocean. And if we do this in the area of a downwelling eddy, a lot of the carbon will get pulled deep into the ocean. I'll talk to you more about downwelling eddies shortly. We would monitor the removal of carbon dioxide with carbon dioxide sensors on ocean buoys and also with the NASA orbiting carbon observatory satellite that measures carbon dioxide at the surface. We would also use uncrewed autonomous vessels or drones with more sensing equipment to monitor fish and other parameters. Now, downwelling eddies can actually be observed from space. It's when the currents get together and cause a swirling in an area as much as hundreds of kilometers in diameter that will transport water near the surface deeper into the ocean. There are both downwelling and upwelling eddies. So where to do this pilot? Well, the Mount Pinatubo volcano occurred in the Philippines back in 1991 and deposited a lot of ash into the South China Sea. We think that doing a test in a 100 kilometer by 100 kilometer area downwind of the location of the volcano is a good place to start. And this is based on seeing that ash cloud from 1991 blowing into the South China Sea as shown here. And you can see that project area right in the middle. And with satellite observations, we know that downwelling eddies occur in that area from time to time. So our target would be in that zone. The buoys that we would use to measure the carbon dioxide at the surface of the ocean are equipped with GPS, solar power, and satellite radio to transmit the data. These buoys are about 16 inches in diameter, and we would use about 25 of them in a grid within the project area, measuring the difference between different buoys to observe the change. We'd also be monitoring with the orbiting carbon observatory satellite, which takes 10-kilometer wide measurements, and we have a way of analyzing that data to show where increases are occurring and where decreases are occurring at the surface. The project is actually low risk. It's doing something that normally happens when iron blows into the sea. It's a small project area relative to the size of the ocean. And the amount of dust that we're depositing is really a low concentration per area. And we would do ecological monitoring to watch for any possible adverse effect, although none have been observed in the past and none are anticipated. We're taking a walk, run, fly approach to the project. That means making sure our monitoring equipment really works the way we expect it to when we take it out into the difficult environment of the ocean 100 kilometers offshore. Then we can scale up to larger tests and eventually scale up to doing carbon dioxide removal in multiple areas around the ocean at the rate of removing 60 gigatons a year to reverse the effects of global warming. Monitoring we will do will first be to measure how much carbon dioxide is actually being removed. Second, we need to monitor any potential effects on habitats and species and also show whether the phytoplankton growth is indeed contributing to the food chain to increase fish production and reduce the problem with ocean acidification. We want to do this in a way that's socially acceptable, and we do this by complying with environmental regulations. There's also measurements that can be taken to earn carbon credits, but that's not part of our scope. We're not part of the carbon market. There's also academic research being done on how exactly dust and iron are used in the ocean and how the phytoplankton interact with other species, but that is not part of our scope again. We're focused on the first three. In order to get permission to do this work, we're going to need an EPA permit under the Marine Protection Research and Sanctuaries Act, and this helps to comply with the London Protocol, if you've heard of that. These requirements are outlined on the EPA website, and the EPA also explains that there are two other carbon dioxide removal projects for which permit applications have been approved, and we're using those as templates for our application. We've got a strong team that includes a chief executive officer who has previously worked on carbon dioxide removal. I'm an environmental engineer. Peter and Carol co-authored the book on climate restoration. Dr. Alan Burnham is a PhD physical chemist, recently retired from Lawrence Livermore National Lab. Joe Brabeck is our Chief Technology Officer with a background in hardware and software. And Marcus Cooper was in the Navy where he did logistics work, and that forms our core team that is helping to move the work forward. We've accomplished a lot this year, including testing the buoys with the CO2 sensors, developing the algorithm for the data analysis of the satellite data, putting together a couple of papers on the science and methodology, some presentations at the Institute of Electrical and Electronic Engineers and other conferences, and we've met with the EPA staff. Our work has been enabled by an initial $100,000 donation earlier this year, and we're planning to do more work this year on refining the buoys and sensors, lab testing the iron material, and getting that permit application submitted for approval in 2026. The EPA review process is a minimum of 6 months. Early in 2026, we'd also like to secure the $500,000 that we estimate is needed for the ocean testing west of California later in the year. And then with a small amount of iron under that EPA permit, be able to see how our equipment works. Then we'll be in a position in 2027 to do some further testing of effectiveness and safety, and ultimately get into a position to refine our budget for a large 100-kilometer by 100-kilometer pilot, which we think is going to be in the order of $5 to $10 million, but we need to sharpen our pencils on that. Ultimately, we think it's going to take 500 million to a billion per year from 2030 to 2050 to remove that 60 gigatons per year of carbon dioxide from the atmosphere. But that's really only a thousandth of the estimated environmental damage and economic impact that's happening annually from global warming. The greatest failure of all, of course, is the failure to act when action is needed. And you might have thought that it was a politician that said that, but it's really an American basketball coach. You can help by telling others about climate restoration, learning more about it via the links at our website, making a charitable contribution to help support the work, and contributing help in areas of marine biology, oceanography, and data analysis. Here's some ways to get in touch with us, and I'll put up a QR code so you can find our website easily. Appreciate your time. Thank you for listening, and we'll look forward to hearing from you.